I have the pleasure to introduce to you the topic, or at least, or the understanding of how I see how large language models will influence how we will deal with knowledge and data in companies, but any kind of organization. And in order to proper motivate this topic, I brought to you two small statistics that may or may not be fully true. But the important aspect here is that knowledge management in general has an impact on how management organizations are run. And on one hand, we see that development time, especially in engineering fields, are highly dependent on the efficiency how we deal with knowledge within our companies. So basically, we have, or a lot of our time basically goes into information retrieval. So where do I get what information at what time? And we have a lot of synchronization meetings. I think every one of you have a feeling what that means. And finally, we have also the question of responsibilities, which usually are also decided within meetings, and they are oftentimes buried under the information that are covered there. And on the other side, we also have the question of mistakes. So a very illustrative example that shows how companies usually do not learn from their mistakes, and which shows that 60% of our mistakes that we do in our companies are repeated mistakes. So they have been done before and could be avoided if the knowledge would be present at all institutions or units or workers in the company. And this brings me to the question of how is that even possible today? So we have enough information, at least if we look at the numbers alone, because they are increasing, or yeah, they are increasing rapidly. I think everyone knows this. We have, for example, over 9.9 million clients in a bank. And for each of them, we have at least one entry that describes what the client does and how it behaves in the organization. We have sensors in vehicles, so over 150 in a single car. We have over 300,000 entries in a pharmaceutical database, or 12,000 entries in a German genome phenome archive. And what I want to say with this is that the information that is available is there either within the company or outside of the company, so in public available data sets. So the question now becomes, how can we deal with this amount of information, and how can we use it to extract knowledge in an efficient way so that the success of the company can be achieved? And in order to solve this problem, the answer is data and knowledge management. At least that's what is believed to be true. And in order to understand how data and knowledge is a little bit, how they are intertwined or how they're related to each other, there's one model from Klaus North. It's already kind of old, but it gives an understanding of how these elements are related to each other. So we have below, in the level below, we have the data, and above we have the knowledge. So what we see here already is that knowledge basically depends on the data. It builds upon the data. And how this basically evolves is we have on the most bottom side, we have our characters, which if we give them some form of syntax, so some form of rule, how these characters need to be read, we create the data. Or we receive the data. With data and the semantics, so some form of meaning, we get information. With the information and some form of learning how to use them, we receive knowledge. So some form of experience. We use that, not experience, but a connection. So if we connect the information and use them from multiple sources, we receive knowledge. This knowledge basically can then be used in some form of application to gain action. So we can use our knowledge to act upon a situation. Finally, if we do our action correct, so basically doing some random actions or doing an action that solves some form of problem, results in expertise. And if we do this expertise so well that no one else is able to solve or do it in a similar way, then we receive competitiveness. And this is where I want to go. So the aim of most companies is, of course, competitiveness, uniqueness, some form of selling, some form of unique selling point. And this basically brings us to why this whole topic is a management topic, because we have some form of strategic perspective on that. We have a strategic goal of a company or an organization that asks the question, if I want to be competitive in a certain economical environment, how does my knowledge need to look like? How does my data need to look like? And this is basically strategic performance that tries to design the elements of knowledge and data in a way that it results in competitiveness. On the other side, of course, there is some operational perspective too. This is just like, how do I organize, how do I structure my characters so that it becomes data? How do I build the data pipelines that I receive information? How do I connect information to gain knowledge? And how do I bring that into action? So this is like, how do I design my pipelines, my workflow within my organization? And with this kind of understanding of how what knowledge management is in theory, let's take a look at some practices from engineering companies. I brought four. They seem to be like some form of known best practices. And I think they are also some are maybe new, some are maybe a little bit not that new. Um, for example, we have in Bosch a senior consultant that retired. So basically, these are experts that have already been retired and they are still offered some form of consultancy position. So they can be consulted regarding their expertise, although they are, of course, retired. And this ensures that the knowledge that was captured or lives inside the senior consultant can still be exchanged or retrieved, especially between generations, because we all know with the demographic change, these people are falling or they are leaving the company year by year. We also have another concept called expert debriefing. This is also a very classic idea. So basically, experts are regularly interviewed regarding their knowledge. So there are some knowledge managers who try to extract as much knowledge as possible from these experts, and then they document them in some form of knowledge base. This, of course, ensures that the expertise is kept also within the company and make accessible also beside the experts. How can such knowledge bases look like? Well, most companies work with some form of wikis or blogs. They are just written data storages where everyone and anyone in the company can contribute. They require heavy maintenance and a very strong knowledge sharing culture. And what often happens is that in the beginning, the wikis are built fairly quickly. Everyone dumps their knowledge into this wiki, and after a while, without proper care, the knowledge becomes outdated, the sharing becomes lower, and the usefulness also declines. But if this is done proper, with enough maintenance, this knowledge platform, wiki, enables the sharing of knowledge for everyone, from everyone, which also improves, of course, motivation, visibility, and better describes or gives the people more empowerment regarding what they know within the company. Finally, we have also some form of expert exchange. This is also very special. there, the idea is to bring in multiple experts from different departments to work together on an internal problem. So this can be, usually these problems are very interdisciplinary. They are focused on problems that cover multiple disciplines, multiple departments, and these experts try to work together and solve these problems. They get, of course, some time to do so, propose some form of project proposal, and in the best case, they come up with a solution that is implemented also directly. These interdisciplinary projects then promote some form of collaboration, and they also foster knowledge exchange. As you may understand, or as you may see, that these experts basically exchange how they see problems, how they work together, and in general, I think this is a very interesting idea to share knowledge also outside of your peers. I think what these four examples illustrate is that we have a lot of expert exchange organizational measures. So we have some form of, or these organizational measures are not focused on the technical aspect. And the major technical solutions are currently most stored or mostly limited to these wikis and blogs where the knowledge is stored in a very simple way. And how we deal with knowledge management is, or how we deal with knowledge is as old as humanity itself. But technological innovations usually had a big impact on how we do so. At the beginning, we had like tools, and in the Stone Age, of course, there was not much to store the knowledge with. But we had at least some tools, some experience, and the corporations and the exchange within the people in smaller groups enabled some form of knowledge management. After a while, we got writing, so some form of paper where the documentation was done through writing and the exchange through language. And this meant that our knowledge could be shared through multiple groups over multiple generations. With the invention of, for example, printing of books, we had the ability to reproduce our knowledge and distribute it globally, which was stored over multiple centuries. And as you can see today, we are in the age of artificial intelligence, where digitalization and algorithms are everywhere, where the knowledge is permanent, lives permanent in the World Wide Web, and is available immediately and everywhere. And this begs the question, how come that knowledge management is relevant today? What is the new technology that I believe will drive knowledge management to a new era? And I believe, of course, and you all may heard of them, is the topic of large language models. And why is that so? It's a very fundamental aspect. I believe that humans, as we have seen so far, or as I know so far, store their knowledge in some form of text. So you write something down and you share that knowledge via language. And the problem with text was before, and is still today, is that it is unstructured data format. It's an unstructured data format that requires the interpretation of humans. So the information that is stored inside a text is not direct readable, and usually requires some form of interpretation of humans. At least this is how it was before humans invented large language models, because large language models are now able to process the text and access that knowledge, and thus access the knowledge that was previously more difficult to extract within the text. And to give an understanding where this comes from, so I just want to give you a quick recap. So basically, the major breakthrough points of large language models is on one hand the data quantity. We have the World Wide Web that provides a data corpus that is big enough to cover almost all aspects of the human language. And on the other side, we have graphic cards, so technological advancements that are basically enable us to train models that are capable to understand or deal with this data quantity. So we have these graphic cards basically are capable to train models with billions of parameters in an efficient manner that was previously not possible. And finally, there is the transformer architecture that uses the attention mechanism to compute all these the relationships between sentences and words or tokens in a parallel manner. So here the parallelism of the computation steps is the major breakthrough point that enabled graphic cards to deal with the data quantity. And so how does this attention mechanism work? And how can it be used for knowledge management? Well, on one hand, we have to understand that attention contextualizes embedding vectors based on their context. And what that means is if we look at embedding vectors or word embeddings on the left side, we can see that some words or meanings or that the words are translated into vectors, which then are which have some form of meaning in an embedding space. In simple, if we take the word king, subtract man, and add woman to it, we receive queen. Or at least a vector that is close to queen. And the transformer does exactly this. It translates or it changes a vector in the word embedding space in a way that it ends up in a place that has a meaning or that has a semantic meaning and describes the sentence behind it. So it translates basically the sentence into a space that describes its meaning. And what we can then use, or what we can then do with it, is we can compare these vector spaces or these vectors in order to answer questions. For example, if I ask the question, what is all I need? Then I can translate this into a vector space and then compare the next vector that is the most close to this question in order to receive an answer. And this would be attention is all you need. This technology can then be used for document or information retrieval. And this is done in so-called retrieval augmented generation solutions. So we take our documents, we translate them into embeddings and store them in a database. And then we compare the request of the user using a vector comparison, in short, cosine similarity, and basically retrieve the right passages in the document, give them together with the request to a large language model, and receive an answer that is built based on the information that we retrieve from our database. So we basically use our documents to then retrieve information, or in this case, knowledge. Yes, and however, these RAG systems are limited in their ability to answer holistic questions. So this means that RAG systems basically just compare vectors, and they basically search within the document sentences that sound the most similar to the question that you asked. And this works really well with facts. So if I want to know some certain facts, then my question sounds very similar to my answer. But what if I want to ask more holistic questions? So questions that go above facts, that basically combines multiple information from different sources. And in order to do that, let's take a look at Google. How does Google give you more information that you basically asked for? If you look at this example, if you type in Marie Curie, you get like pictures of her, you get like some background information, Wikipedia articles, and also relatives. And how does Google do this? Well, it works with knowledge graphs. So what does a knowledge graph do? We have some form of, instead of just vectors, we have some form of entities. And these entities have some form of class and a name. And then there is some metadata behind these entities. So when it was born, when the person was born, when it was deceased, and also relationships. Because if there are different entities, then between them there can also be some form of relationships. In this case, for example, her husband, Pierre Curie. And both were awarded with Nobel Prizes in physics. And finally, if we look at all our Nobel Prize winners in the last years, we can of course also see that Albert Einstein also won one. And this allows us to also find other entities that are related to, for example, the person Marie Curie. And this is how basically Google gives you the extra information. It traverses these knowledge graphs and finds the most relevant information and puts them additionally on the right side, for example. And if we want to, or how are these knowledge graphs now dealt like technically? Well, they are stored in some form of knowledge or graph databases. And these graph databases then can be accessed via query languages or some form of languages. But conceptually, let's take a look. We have on the bottom side some form of document level, on the top side some form of semantic level. These are all represented by edges and nodes. So we have our document at the bottom, which itself represented as a node. And then we have chunks, so text chunks that are ordered, for example, or correlated, that are first well within the document, of course, and then they are also correlated in the way that they describe how they are followed. So we have chunk that is followed by the next chunk and followed by the next chunk. And each of these chunks, of course, have also an embedding that describes some form of meaning. As we said before, this is a vector representation of the text. And these basically in these chunks, for example, we have some persons, maybe an award, and these are also edges. And these persons then are basically awarded or not, or mentioned in these text chunks. So we can basically use a knowledge graph to describe not only the semantic level, but also the document level. And how this is designed is basically specified in a graph schema, which entity classes exist, what relationship types can exist, graph generation rules, and other attributes, and which basically defines how this whole graph database does look like. And this is then used in our RAG system. So we basically only replace the vector database before with our graph vector graph database. And the process is the same. We have some documents that use an embedding model to translate them into chunks. And they are then stored in entities. And so we basically have the embeddings, and they are then stored in the entities that are related to it. And then and between these entities, we have our relations. And what we do now is we do a vector comparison, right, from our RAG system user. This basically searches inside our graph vector database to the right embedding, and then takes all the embeddings that are related to that entity, that are close enough, and gives them as chunks together with the request back to the large language model, which then produces an answer for our user. And what we can see here already is that we not only receive the vector that is most close to our question or our request, but also from other entities. So embeddings from other entities that are close related to our request. And hopefully this improves, or at least within the literature, we can see that it improves the accuracy of our answer. It simplifies our development because we are better able to structure our solution. So if we build a graph RAG system, then it's easier for us to develop test, just to test our solution, because we can better explain or understand how the chatbot or the large language model generated our answer, because we see basically all the relationships that is built within the graph database. And we can also modify this, right? If we see some form of misbehavior, some form of wrong relationship between entities, then we can adjust this graph database through the language, of course, in order to adjust the performance or control which kind of knowledge or information the LLM uses. And in this case, of course, I want to highlight, or not highlight, but I want to remember that, remind that all these information that the large language model uses for answering is all built from the documents that we have available for ourselves. And the problem now is that the knowledge graphs that we have to build, they are a big bottleneck, right? If the building the knowledge graph would be so easy, then we wouldn't even need probably large language models. But the problem now, or the solution now, is that, or one innovation is now that the LLMs are also capable to build knowledge graphs. And this, of course, simplifies the generation of or structuring the documents into knowledge entities. And how does an LLM does this? One approach is to first we do some form of chunking. Then we ask the LLM, hey, can you read out what entities are within your text message passage, and also define the relationships between them. And if this works, then the LLM then can also ask, like, based on all these relationships, how does the schema look like, and how does the knowledge graph for all these entities look like? Finally, we can also ask the large language model to build communities. So given all these entities and the knowledge graphs, what are communities that are most probably together? The question, of course, now is, what is a community? A community are entities that are close in semantic meaning. So that are basically, for example, let's take the example of the Nobel Prize winners. Of course, all Nobel Prize winners, all people that won a Nobel Prize, they could form a community. And then we can let the LLM generate a community summary that basically gives an overview about the community, who are the people, what are their properties. And this allows then the LLM to generate a more holistic answer, because it has not only the information of the entity itself, but also a summary of how all these communities, how all the entities within the community work together or are related to each other. And this community building is, of course, not limited to one entity or the level of entities. You can also build communities above communities. And of course, with each community layer, your information density or the amount of information that is covered by the community, of course, increases, but the level of detail, of course, decreases. Yes, anyhow, the large language model then produces the answer, and the user can basically see it through the RAG system. Okay, let's summarize quickly what we have discussed so far. So we have explicit knowledge is documented in a text form, and thus their usage is available only under high cost. And large language models are capable to structure this text semantically. So it was unstructured before, and it structures them into an embedding space. So we basically translate before unstructured text into a vector space that has a semantic meaning. Then we can use these large language models to build graph RAG systems that use these graph databases to combine large language models with available expert knowledge. Why? Because we have the expert knowledge stored in some form of text bases. These are then translated into a graph, or these are made available to the GraphRag system through a graph database, and then the user basically can use the large language models to ask questions regarding the knowledge that we have stored. And now I've talked a lot about knowledge management in large language models. Now the question, of course, becomes, okay, how does data management affect the whole system? And if we look at data management and how it could improve GraphRag systems, we can see multiple improvements, but I brought these four with today. We have governance, no, provenance. So basically the ownership of data sets that is designed through the data provenance or proper data management. And what this does is basically it improves the trustworthiness of edges and nodes. So it enables us to trace back what the answers of our GraphRag system allows us to do. Or no, it traces back basically who stored the knowledge inside our knowledge base slash graph. And this basically improves the output, the trust in the outputs of our AI system, for example. We have the topic of metadata. So proper data management basically now enables or tries to provide fair metadata, tries to implement fair metadata principles. And these metadata in general improves the contextualization of knowledge graph edges. This means that in general, if I know more about my data that is available, it gives the knowledge graph more information that can be used to build the knowledge graph. This is a simple example with Marie Curie, for example. We had the metadata of when she was born and, for example, when she deceased. And based on these, of course, you can build new connections, right, with other people that were born at the same year, for example. And this, of course, so basically with metadata, you build a new layer on top of your data set itself that allows you to build connections in the first place. And this, or semantic connections. And this allows us to better retrieve text chunks, for example, through a better ranking system. The third aspect would be interoperability. So if we standardize the data schemas that we have available to us and build ontologies or vocabularies, we are better able to integrate heterogeneous data sets. And if we do so, allows basically in our GraphRag system the connection of different data sets, which in our case was only text, but you could also think about other data sets with the right metadata that describes our data sets, which then allows us to combine these findings in one data set with, for example, a text chunk in another data storage, which then allows us to do some form of multimodal reasoning. So we get not only information from text, but also, for example, from a data set, which of course for industrial application is highly relevant. Then we have some smaller aspect, but also important, the question of version control. So if we do proper version control of data set changes, we basically allow some form of temporal graph reasoning. Or in other terms, we are able to observe how our knowledge evolves over time. We are able to also observe how our knowledge graph evolves over time. And this basically covers some form of, in machine learning, there's a term called model shift or time shift. And this also basically can happen with, for example, the knowledge shift in our GraphRag system. And by tracking this, we are able to track back where, for example, changes were that were not helpful for our GraphRag system, for example. Okay, and on the other way around, how can large language models improve data management? I think here probably the audience may know a little bit more than my quick search did, but I think the four big aspects that I at least see here are the biggest potential is the metadata creation itself. So large language models can, of course, can be used to describe or to support in describing the dataset that is there. Of course, we still need the expert to do so, but with enough of keywords or descriptors, it can generate a text that describes the metadata fairly quickly. We have some form of semantic integration. So what you can ask a large language model to do is to basically combine different data sets to integrate them by using the metadata that you have designed before. So you can, if you know metadata or the meta information about a data set in a, let's say, language or natural language understanding way, you can ask it large language models to combine these data sets, how they can be interpreted together. Then we have the question of data governance. So this is just a question of, okay, if we have a lot of different policies that basically define compliances regarding monitoring or data sharing, then we can basically build a solution that tracks automatically or that interacts with the user regarding these policies, which gives the user more trust in, for example, whether he's allowed to share the data, whether he's allowed or how he should deal with the data. So what kind of things he's allowed to do and what not. And for example, you can design some form of chatbot that assists in these questions, because all these documents are very dense and they have a lot of information hidden there, and some large language models could help to interpret and summarize these. Finally, we have also the intelligent search, and this brings us completely back to the knowledge management. So the question of findability of the data set. So how do I find the right data set? And here, for example, you could use some form of natural language to describe what you're looking for. And this queries the database then automatically based on your input. And of course, this requires, or what a technology that could be used here, for example, would be a GraphRag system that has the metadata, that uses natural language to find the right descriptors to the query or the request that you send. For example, I'm asking for a data set regarding temperature of a machine sensor. Then, of course, you need some form of metadata that describes, okay, this is a machine sensor. And then it could use, for example, a RAG or GraphRag system to retrieve the data set that was stored in our graph database. Okay, now I talked a lot for 40 minutes. I want to finally conclude with what I want to say. And I want to bring you my last statement. So basically, the way we manage our data today will impact how we will access knowledge tomorrow.